going to discuss hybrid circuits. Hybrid circuits are circuits that have connections of resistors that are of a series nature, one right after the other. And in another part of the circuit, there may be resistors that are connected in parallel, where the current branches, part going one way, the remainder going the other. Look at this circuit. We have a 60-volt power supply, another word for a battery. And then you can see the various resistances. The current that comes out of the battery travels through the 4 ohm resistor and then approaches branch point B. Some goes upstairs, the remainder downstairs. The two currents in the parallel resistors combine at branch point A, equaling whatever approached branch point B. And then that current travels through the 2 ohm resistor and then back to the battery, and then it repeats. Our goal is to determine first the current out of the battery. Whenever you're asked to determine the current out of a battery in a hybrid circuit or even a simpler circuit, what you want to do is to find the equivalent circuit. The equivalent circuit is, in your imagination, the battery with one so-called equivalent resistance. Its resistance, as far as the battery is concerned, might just as well be there in a simple circuit. It's the same as the case for the more complicated circuit. So we do that by slowly reducing the circuit step by step until we only have one equivalent resistance standing. Well, I invite you to consider the following procedure. Between points A and B, we have two resistors in parallel. Now, in a previous lecture, I showed you how to find the equivalent resistance of a pair of resistors in parallel. The rule is the product divided by the sum. The product of the two resistances, then divide by the sum of the two resistances. So we have, for the 6 and the 12, the product is 6 times 12, or 72, and the sum is 18. Product over the sum is 72 over 18, 4 ohms. So as far as the battery is concerned, you might just as well take out these two resistors between points A and B in the circuit and put a single resistor whose resistance is 4 ohms. I've done that here. I've repeated the circuit, 60 volts, 4 ohms, and then replaced this pair with the 4 ohm resistor, and then the 2 ohm remains. What we have now are 3 resistors connected in series. We know they're in series because, well, look, whatever current comes out of the battery has to go to the right, turns up, turns left. It all goes through the 4 ohm resistor. It all goes through this equivalent resistance and then continues on and goes all the way through the 2 ohms. So they're all in series. And the rule is this: for series connected resistors, the equivalent resistance is a sum of the several. Sum of 4 plus 4 plus 2 is 10 ohms. So now I'll remove all of the resistors in this circuit and maintain that as far as the battery is concerned, it might just as well be a single resistor whose resistance is 4 plus 4 plus 2, or 10 ohms. That circuit is shown here. The 60 ohm battery, it sees equivalently 10 ohms in one resistor. Now, because we have a simple circuit, we can use Ohm's law to find the current out of the battery. It's just the battery voltage, 60 divided by the resistance, 10 ohms. So now we know the current out of the battery is 6 amperes. Now let's take a look at what is happening with the 6 ohm and 12 ohm parallel combination. We know the following. Out of the battery, we have 6 amperes. And so we have 6 amperes here. It divides. Come back to the division later. But it recombines over here, and then it continues on through the 2 ohm resistor, 6 amperes there. Now let's take a look at how the currents branch through the parallel combination. The current approaching the parallel combination, that's point B, is 6 amperes. But that current divides, some upstairs, some downstairs. We use the other divided by the sum rule for the 6 ohm, the upper branch, and we have the other is 12, the sum is 18, 12/18 times the current that approaches the branch point, 6. 6 times 12 is 72. 72 divided by 18 is 4 amperes. So let me report that this current up here is 4 amperes. Now, since 6 ohms approaches branch point B, and 4 of it goes upstairs, what goes through the bottom branch is what's left, which is 2 amperes. Notice that the 4 upstairs and the 2 come together at that point and continue on, adding up to the 6 that were reported earlier. What do we know? We know the current out of the battery is 6 amperes. We know each of the currents in the 4 resistors. If we wanted to, and we don't want to do it now, we could, for our amusement as well as edification, calculate the individual powers consumed in the 4 different resistors using the I squared R equation, which you probably forgot all about. But the power consumed by a resistor is the current squared, I squared, times that resistor's resistance. So it's the I squared R power consumption equation. You can calculate those 4 different powers consumed, add them up to get the total power consumed in the circuit. In a previous lecture, I told you by the energy conservation idea that whatever is the power produced, that's the total power consumed. The power produced is the power produced by the battery. And that power produced is found using the pi equation. The power consumed is the current out of the battery, 6 amperes, times the EMF of the battery, 60 volts. So it's pi I, which is 6, times the EMF is 60. 6 times 60 is 360 watts is the power produced. I think it would be a good exercise for you to calculate the separate 4 powers consumed and confirm that the sum of those powers consumed is 360 watts. Any questions?